This next one, this has to do with the de Broglie wavelength. So this has to do with the wave nature of matter. So we have an electron that's moving very quickly, and we want to know what is the contribution of its wave nature. So the de Broglie wavelength is an equation I'll give you, lambda for wavelength equals h over mv. Now, m here is mass. Mass must be in kilograms. And v is velocity, which must be in meters per second. Now, we can deal with this. Now, the problem does not give you the mass of an electron. Don't worry, I'll give that to you. You don't have to memorize it. Okay, but let's use this formula here and make sure our units cancel out. H is Planck's constant, 6.626 times 10 to the negative 34 joule seconds. Next, divide by mass. The mass of an electron, yes, it has to be in kilograms. Oh, the reason this works here, let me define the joule. That's why this has to be this way. These units have to be this way. So here, 1 joule is a kilogram meter squared per second squared. So instead of a joule, I'm going to write a kilogram meter squared per second squared. And then there's a second there for Planck's constant. So that takes care of one of those seconds. Now, let's divide by kilograms. That's why the electron has to be in kilograms. So that's going to be 9.11 times 10 to the negative 31 kilograms. So that's going to be, you can just write yourself, mass of 1 electron. Okay, so that cancels out the kilogram. Now, velocity. This is not speed of light. This is how fast this particle is traveling. So make sure you switch correctly from horizontal units to vertical fractions. So 1.35 times 10 to the 5th meters per second. And that's going to cancel out our other seconds. And that's going to cancel out one of our meters. So everything is canceled except for 1 meters. 1 unit of meter. That's a unit of length, which is appropriate for a wavelength. So let's go ahead and see what kind of answer we get. So here we're going to get Planck's constant divided by 9.11 times 10 to the negative 31. And then we need to divide by 1.35 times 10 to the 5th. So that's going to give me 5.39 times 10 to the negative 9. 5.39 times 10 to the negative 9 meters. If you say, oh, hey, that negative 9 there looks a lot like a nano, you'd be correct. You could say 5.39 nanometers if you do that. It doesn't specify what unit it wants, so both of these are correct. This is actually a pretty measurable quantity. So, you could really do a lot with that. So this is telling you that the electron has a pretty substantial wave nature that needs to be accounted for. Now let's take this other example here. We are firing a .22 caliber bullet, and it's moving pretty fast. It's heavy. It's a lot heavier than an electron, but it's not that heavy. It's light. I think a bullet packs a lot of energy, and we want to calculate the de Broglie wavelength of this. So we're going to use the same principle here, lambda h over mass times velocity. So we may have to do some converting as we go along. Times 10 to the negative 34. Kilogram meter squared seconds over seconds squared. So yes, I know that seems weird, but write it that way anyway. Now, we need to divide by the mass. We're given 1.9 grams. We don't need grams, we need kilograms. So let's go ahead and make the conversion. 1,000 grams is 1 kilogram. Now all of those are gone. Now we need to divide by the velocity, 765 meters per second. Okay, the only unit left is meters. So let's take Planck's constant. Can't see that. Planck's constant times 1,000, divide by 1.9, and divide by 765. So this gives 4.56 times 10 to the negative 34 nanometers. Now, if you look on your big electromagnetic spectrum, you're going to go, yeah, it's not really on there. So a bullet does not really have any considerable wave nature that we need to be considering.